Hello, welcome to the week 12 lecture. So this lecture is pretty straightforward on equations. So about half the equations that you're going to need are on the board right now. But because it's straightforward on the equations, I'm going to spend some time going over some examples. And then some of these examples are what you should study for uh, the problem for this chapter on this test, on the next test. So, what is static equilibrium? Static equilibrium is what we're concerned about, and it's what happens when a system isn't moving or is moving with, or a system isn't moving. So in order to have static equilibrium, you have to have no acceleration and no angular acceleration. So if there's no acceleration, that means that F equals ma is 0. And if there's no or if there's no linear acceleration rather, and if there's no angular acceleration, that means torque, the net torque is equal to 0. So this is pretty straightforward because torque causes a change in angular acceleration and F causes a change in linear acceleration. It would make sense that if you're having neither of those values change, then those forces and those torques have to add up to equal 0. So F net has to equal 0. So the only wrench that I can kind of consider is that what if you change the origin? What if instead of saying 0 is here and measuring all the torques around here, you say 0 is at this point and measure all the torques around here? They're going to have different torques because they have different positions. So the distance from your initial position, the R is going to be different. So that means that you're going to have different torques for each position. But if that's the case, first of all, let's just say F, if we change the origin from R prime to R minus some new vector R, where R is a constant, the big R is a constant. If this is a constant vector. Then the FK is still going to be 0 because changing the origin doesn't change anything about your forces. It doesn't like come into the equation when you are defining forces, but it does come into the equation when you're defining torques. So in order to prove that we can just change from R little r of our initial system to R prime, where prime means that it's a new system. So R prime goes to equals R minus R that constant R. Tau goes to tau prime, where tau prime is going to be equal to R uh, K minus the big constant R cross Fk for each of the constituent particles. And then F goes to F prime. So F prime is still going to be equal to 0. So as tau prime equals R, sum of Rk minus big R cross Fk, we can break that up into sum of Rk cross Fk minus big R cross R cross sig Fk. And then because this first term is going to just go to your initial sum of torques that you had, which and then this second term is going to go have some constant outside. So we can remove it from the summation because it's a constant cross the sum of all forces in K. So you have if is 0 in S is 0 in S prime, the new whatchamacallit, the new coordinate system. So if torque sum of the torque K, so the original torques is going to be equal to 0 because we're talking about static equilibrium. So in this case, the original torques are equal to 0 because that was our state for there being static equilibrium. And then R cross the sum of the original forces is going to be equal to 0 because the sum of the original forces is also equal to 0. So this is 0 minus 0, which is equal to 0. So if the sum of all of the torques in one origin frame are 0, then they're going to be different. They're going to be the same in another origin frame where you change your value for the initial R. So that's, or you change your value for your origin is what I should say. So that's basically all you need to know for static equilibrium. Uh, just before we do any examples, I want to go over some vectors which are pointing into the page versus pointing out of the page. So we know that if you have a vector that's pointing along the page, it's just an arrow. But part of it is pointing into the page, then we use this arrow, this circle with a cross sign in it. And if it's pointing out of the page, we use this circle with a dot in it because it's supposed to look uh, like an arrow that's being shot. So the notch side would be the cross side, the side where you place the back of the arrow into the notched into the bow is going to be the cross side, and then the pointy side is going to be the one with the dot in it, and that's going to be pointing out of the page, so that's the front side of the arrow. So yeah, that's just something that's useful to know. I'm going to save this real quick and then move on to our examples. So um, one of the examples, one of the things that happens is that uh, when we're talking about torque, this isn't exactly static equilibrium, but basically, when we have a truck that's moving, that's leaning to the side, this is something that we also should consider. Uh, what we need to worry about, uh, whether or not it will tip over is whether the truck's center of gravity is pointing uh over the tires or under the tires. So we actually need to make this truck bigger in order to get my point across. But if the center of gravity is here, then this is stable because the force due to gravity is going to be pointing uh, down less than the tires themselves. So it's going to be pointing down and it's going to be pointing in an area that's uh, going to be it's going to be pointing down, and then there's not going to be a torque that's pushing it, pulling it down to the side because this center of gravity is going to be above the pivot. It's going to be above the area where the torque is, or where the wheels are going to be pivoting. So since it's a uh, between the center of the mass, or not the center of the mass, the center of the truck and the wheels, it's stable. But if the center of mass, if you put it up here, if it's a high center of mass, then if it tips over the same angle, then uh it's going to be on the side. It's going to be on the side of these wheels, and it's going to have a torque that's exerted uh, to the side of the wheels. Uh, so that torque is going to cause there to be a pivot to the right, which means that it's going to tip over. So basically, what you need to know is what side of the wheels, or what side of the base of the system uh, a torque is going to be in. So where is the center of gravity going to be pulled down? And if it's on the inside of the wheels or the inside of the base, then it's stable. If it's on the outside of the base, then it's unstable. So these are centers of gravity, which are essentially centers of mass for small objects. So small objects means like smaller than a mountain, basically. So uh that's that's why I want to get to through with that. So in order to find the center of mass, we can have a car with 52% of the weight supported by the front wheel, and 48% of the weight supported by the back wheel. And we want to find the distance between the center of mass and the center of mass and each of the wheels and the back wheel, basically. So this is X, and then this distance is d. So in order to set this up, we have the condition that all of the forces are equal to 0. So when we draw the free body diagram, we're going to have normal force on the car pushing up, normal force pushing up on the front wheel and the back wheel by 0.52 weight and 0.48 weight. And then there's going to be a weight from somewhere in the center of mass, which is going to be pulling down in this direction. So when it comes to forces, all we have to say is that positive 0.52 weight plus positive 4.48 weight minus W equals 0. So if that's the case, then uh, 0 times W equals 0. So this is true for any weight. So this is just a sanity check, basically, that we divvied up our uh, yeah, that we divvied up our uh, weight evenly, and that the weight pushing up, the normal force pushing up, is equal to the normal force pull or the weight of the car pulling down. So how about the torque? So we have sigma of torques of any kind, sigma torque K, is equal to uh, R cross P. Oh, so the thing that I need to note, the first thing that I need to note is that we're pivoting around this point center of mass. So it always helps to have one of your centers of masses it nor not a centers of masses, but it helps to have your origin at one of the forces, so you don't have to calculate that force when you're doing the torque. So in this case, I'm going to place the origin at the center of mass. So sigma tk is going to be equal to r cross 0.48 weight in the uh, coming out of the page. So this torque is coming out of the page. So let's call that a negative torque equals negative 0.48 times x sine of 90 degrees, because you remember that torque equals FD sine theta. So the magnitude of torque is equal to F times the distance from the origin to your force times sine of theta, plus the torque pointing in the other way. So R is going to be pointing to the left. Torque is going to be pointing up. So we end up with a torque pointing into the page. So let's make that 0.52 times x minus d times sine 90 degrees, because that is also perpendicular to the axis and the axis and the whatchamacallums, and the forces are perpendicular for both of these. So this is going to be negative 0.48 x plus 0.52 x times, oh, and then times weight, of course, minus 0.52 d times weight is equal to 0. And then this is weight times 0.52 minus 4.48 x minus 0.52 d is equal to 0. So for any weight, this is going to be true. So we can just cancel out the weight and then say 0.52 minus 0.48 is going to be 0.04 x minus 0.52 d equals 0. So x is going to be equal where did I get it? And then x is going to be equal to whatever gives you that value. Oh, oh. It's x minus d, not d minus x. Oh, yeah, that's going to change some things. Sorry, let me just rewrite the math. X minus d, not d minus x, or d minus x, not x minus d, equals negative 0.48 plus 0.52 weight times x plus 0.52 d. So d times weight. So equals negative weight times x equals 0.52 weight times d equals 0.52 d minus x equals 0. So so x is going to equal 0.52 d, which is a lot more reasonable number than what I was getting earlier. So yeah, that's how you find a basic statics problem. We're going to do 2 more statics problems, and then I'm going to go to the next section. So clear this out. Next problem is a torque balance. So you have weights on one side, M1, M2, with 30 centimeters between them. 40 centimeters between weight 2 and the pivot, which is this is the pivot, so it's being held on this uh it's being held here, and it's in equilibrium, so it's not moving, so it's just resting on top of it. And then 30 centimeters between here and the third weight, which is going to balance out this other two. So I'm not going to worry about the normal force. That's a problem in the book. What I'm going to worry about is the total torque being equal to 0. So again, doing the right hand rule, R to the left cross F, the force of gravity pulling down is going to give you uh a resultant force pointing out. So pointing out. So these are both pointing out, and then this one's going to be pointing in because they have forces of M1G, M2G, and M3G. So actually, let's just do the normal force from the spike if we want to. So this is going to have normal force. So sigma Fk is going to be equal to normal force minus M1G minus M2G minus M3G is equal to 0. So normal force is going to be equal to the sum of the weights. So we don't know M3G yet, but we're going to solve that using the actually useful data that we get from looking at the torque. So sum of the torques in K for each individual torque is going to be let's have pointing out the page being the positive direction, M1, and then this is going to be our pivot because we want to get rid of normal force. We don't know what normal force is necessarily. So we can just ignore normal force altogether when we're trying to solve for M3G. We're trying to solve for M3. And then these two are known. 1 equals 50 kilograms, M2 equals 75.0 grams. So this is going to be equal to M1G times 70 centimeters because that's the distance from this pivot to M1 plus M2G times 40 centimeters minus M3G times 30 centimeters, which is equal to 0. So we know M1, we know G. We can just cancel out G, honestly. So M1, 50 times 70 plus 75 times 40 equals M3 times 30. And then, of course, know that M3 has an opposite sign because it's pointing in the opposite direction. So you need to figure out whether it's pointing into the page, out of the page, or whatever you have using the right hand rule. So M3 is equal to 50 times 70 plus 75 times 40 divided by 30, which is equal to 317 grams. So you need that much weight in order to uh, balance out this torque balance. So I don't know if you've used like old scale weights, but this is similar to what they do. So when you have M3 is what you're measuring, and then you move the balances of M1, M2, M3, like the whatever forces are on the other side of the balance. And then once you cancel out the torque, that's going to be able to solve if you use your algebra right, like they did when they were designing it, it's going to be able to solve for M3 in the same way that we solve for M3 here. So that is the thing, and then normal force is just the sum of the weights, which is going to be equal to uh 50 plus 75 plus 317, or point zero, because instead of working with kilograms, we're working with grams, so we need to divide by 1,000 if we want to get back into our SI units, times 9.8 meters per second squared. So that's also going to be the value that you get. Okay, so last thing before I move on to bulk moduluses and stress, it's just going to be a ladder resting up against a wall. So the wall is frictionless and it has a normal force pointing out this way. The okay, uh for that last one, okay, never mind, just a second. I forgot something. I forgot something very important. In addition to all of these weights, you also have to worry about the weight of the meter stick itself, which is going to have some weight pulling down at its center of mass. So right here at the 50 centimeters from the edge, 50 centimeters from either edge, so 20 centimeters from the fulcrum, from the point that we're pivoting at. So that is going to be plus mg times 20 centimeters. So when we solve for M3, it's going to be equal to M1 times 70 plus M2 times 40 plus M times 20 divided by 30. So if M equals 150 grams, then this is going to end up being 317 grams. So that's going to give us the value. So yeah, sorry about that. That was major uh that was a major oversight on my part. But if this type of problem does come up on the test, you will have to account for the mass of the meter stick. So let's again go back to uh our ladder propped up against a wall. So you have normal force from the ground pulling up and then friction also from the ground pulling to the side. Uh, and then it's going to have a weight halfway up the ladder and a force pushing to the side as it rests against the whatchamacallit, as it rests against the wall. So this angle is going to be beta. So the angle between here and here is going to be uh pi plus pi over 2 minus beta, and the angle from here to here, or from here to here, where we pretend that this extends out a little more, is going to be equal to pi minus beta. So first we solve, so we want to solve for F. Yeah, sorry. So we want to solve for the force of the wall and for, sorry, just a moment. Sorry. I'm just looking up exactly what I need to solve for. So what it looks like we're solving for is the coefficient of static friction, the minimum coefficient of static friction, in order for this not to fall down. So mu s, and then if this is the limiting case, then F is less than or equal to mu s times n is equal to mu s times n, because we're looking at the limiting case. We're looking for uh the case where if we do this anymore, it's going to, or if we go a little bit lower with our coefficient of static friction, it's going to fall down. So we're looking for it to be exactly equal to mu s times n. So what we need to do is set up Fk is equal to uh, Fx in the x direction and Fy in the y direction. Where I think this is I direction and this is J direction. I think that's the convention we've been using rather than X and Y direction. So, and that's going to be 0x or 0 in the I direction plus 0 in the J direction. So Fx, sigma Fx is equal to F minus F is equal to 0. So F is equal to F. So frictional force is equal to the reactionary force of the wall. Sigma Fy is equal to normal force minus weight. So normal force is equal to the weight of this ladder. So then we do our final thing, which is torque K is equal to 0. Sum of torque K is equal to 0. So if we choose this as our pivot point, then the sum of the torques is going to be equal to R cross is going to be equal to R times F times sine theta. The sum of RF sine theta is going to be equal to L over 2 uh times weight times sine uh 3 pi over 2 minus beta plus length times F times sine pi minus beta. So uh sine of pi minus beta is equal to sine of beta, and then sine of 3 pi over 2 minus beta is equal to cosine of beta. So sigma torque is equal to L times L times cosine beta times weight or negative cosine beta times weight plus F times sine beta. Oh, and then this is over 2 F times sine beta equals 0. So F is equal to weight times cotangent of beta over 2. So we plug this back in. We know that force friction is equal to mu s n is equal to mu s times weight. So F is equal to the force of friction is equal to mu s n is equal to mu s times the weight. So mu s is going to be equal to cotangent of beta over 2. And then, yeah, I think that checks out. So that's not exactly what they solved for in the book, but we were trying to solve for mu s, and we did solve for mu s. So I'm going to leave you for a second, and then I'm going to go on about moduluses and strain and stress. Okay, just a moment. Stop recording.